Good morning. I would like to welcome you all to the session, namely Resource Assessment and Development of VPPs. And as you know, this is a very comprehensive topic. Therefore, we had to divide it into two sessions. There is a time allocation, we have 1.5 hours allocated to this session, where we will have 4 speakers speaking as experts of the area. First, we'll get the presentations, which will be 15 minutes each, and this will be followed by a Q&A part, which will be at least 20 minutes. We will take note of your questions, and I will kindly ask you to introduce yourselves before asking the question. We have made a slight change in the order provided in the agenda. First, we will have Mr. Gregory Erdman speaking. Mr. Erdman has been in the wind energy industry for the last 20 years. In early 90s, he worked in NRG as the sales and marketing director. Also was involved in the resource assessment studies of NRG, our colleague, and has been active in the same sector still. He has also held some managerial positions in the same company. Mr. Erdman, please. I'm sorry, I'm having some sound problems.
Sura, thank you. Hi again, my name is Gregory Erdman. I'm from Renewable Energy Systems. It's a pleasure to be here. As our introducer told us, I've been in the wind industry for 20 years, and I've just focused on the last year of the market in Turkey, and realized it's a very different market in developing wind farms than it is in Brazil, China, Europe, and the United States. It's very interesting. What I wanted to talk about today was over the past 10 years with a tremendous growth rate, and I believe that there has been and will be tremendous growth in Turkey over the next few years. And I thought I'd share with you some trends and some best practices that we've had in the United States. So today, first I'll tell you about who Renewable Energy Systems is. I will talk about some of the about reducing uncertainty and the concept of bankability, which I assume many people know about, and I will talk about some of the similar challenges that we have had in the United States. First, I want to make it clear that we have been in the Turkish market for well over 10 or 12 years. And about a year ago, we did make a very big change where we re-strategized, and we will be very strong in Turkey. We have a new logo and a new name of the company, Renewable Energy Systems, but some of you may remember us as NRG Systems. But the bottom line is that we help customers find, understand, and make more renewable energy. Just one more slide about who we are. Again, we've been in the business for 33 years, and we are a pioneer in wind resource assessment. We have systems in over 160 countries, and one of my favorite statistics is that we figured out this year that we conservatively have calculated that we are responsible for over 3,500 wind farms that have been successfully built worldwide, due to the data that was collected from our data loggers and metmasts. So in the past 33 years, we've literally sold millions of data logger sensors and towers combined. So we have a lot of experience. I'd like to make an observation about what we see in the United States market. And I see it's very similar to what's happening in Turkey. First of all, there's there's fast growth. Things are happening very quickly. There's money to be made and people want to get involved with it. There's very large wind farms and will be large wind farms as well too. 50 megawatts, 100 megawatts, 200 megawatts. The spirit here as in America is very entrepreneurial. Being green takes a close second to wanting to make money and create a profitable wind farm. And finally, I think that there are many companies like in the United States that have their own business models of how they want to develop a wind farm. There's probably about 5 different models, but they all have their different measurement metrics and extrapolation models on how they will create the best bankable wind data. So the common goal is to produce what I call investment grade data, data that you can take to the bank for your financing. It's also about reducing uncertainty and that basically we all want to create a successful, profitable wind power plant. So when I say investment grade data, I mean bankability. Again, this is data that you can take to the bank. We have worked with a lot of banks worldwide that in conjunction with the consultants that we work with, these are all well-known banks that have approved and financed wind farms throughout the United States and actually the world. So we're very familiar in that regard. We're also familiar with all the top consulting companies in the world as well. This is just one example. DNV lists our equipment as approved equipment along with a lot of other equipment as well. But it's very important to have that stamp of approval that the equipment is well known and is certified. So I'd like to talk a little bit about some trends in the industry that we see from the United States perspective. I'll start with sensor trends. Excuse me. Probably about 10 years ago, the big trend was that we went from non-calibrated to calibrated anemometers. You have to have a certificate with your anemometer that says it was calibrated at a wind tunnel that was a certified wind tunnel. The general shift over the past few years has now been not only calibrated, but class 1 calibration. So there's several different anemometers that are on the market that have a class 1 certification. But then again, there's a lot of controversy on where they are calibrated. There's different wind tunnels around the world. They're all good, they're all excellent, but different people have different opinions on which wind tunnel is better. And sometimes the differences in wind tunnels can have more of an error than the differences in the actual anemometers themselves. So there will be a debate ongoing on which is the best one. But from our perspective, because we sell a lot of these anemometers, that there are, I always say this to my team, that there's 3 buckets. There's one bucket of the one type of anemometer that the customer absolutely wants, and there's no way that you're going to convince them to use any other type. There's another bucket that has another anemometer that's a class 1 that they will never switch and they want. There's a very large bucket in the middle of customers that don't really care. They just want a class 1 anemometer with a certificate that goes with it. And maybe price is more important to them. But that is a trend that I see continuing. Moving on to data loggers, high-level trends, there's been a new interest in collecting actually 1-second data capture. Only a few years ago, people only wanted 10-minute averaging of the wind data. Now there's a lot of people that actually want to look at all that 1-second samples that made up that 10-minute average. So that it's a lot more data, but afterwards you can dig deeper and get more granular as far as analyzing the data. Of course, we want more channel capacity. A new trend over the past few years that people now want to call the data logger. While we resisted that for many years, people want to call the data logger, that's fine. Renewable NRG Systems has a position on that, however. We feel best practices that you should not call your logger unless you absolutely have to, but you should have your logger call you once a day and download data. That makes it safer and more trackable and a lot more organized. But again, our data loggers do allow you to call them to upload firmware and other reasons. More flexibility, more software oriented. Obviously, software has come a long way in the old days of data loggers, and there's a lot more flexibility there. The last bullet here is really important, that the data loggers are now becoming more purpose-built, and that means that they are data loggers specifically designed for wind resource assessment. They are not generic loggers that are used for many different other industries and adapted to wind. So there are several very good data loggers on the market that are built specifically for wind resource assessment. I'll move on to Met Tower trends. This is really important. As we all know, we want to start measuring towards the hub height of a turbine. That's the best practice. But turbine hub heights are getting higher too, so it's becoming a practical and economical consideration of how high you want to put a tower. Believe it or not, in the United States, we still use a lot of 60-meter towers, and there is a difference of opinion that you should only be using 80-meter towers. But in the United States, where there's a lot of successful, profitable wind farms, they were built by data from 60-meter towers. And today, 75% of Met towers in the USA are 60 meters. They're practical, they're economical, they're bankable. And when I understand the market in Turkey, when you're in your phase one measurement campaign before you're bidding on projects, 60 meters is approved by MGM and is an excellent way to save money and get very good data. So we recommend that still. 80 meters, of course, are very important. When you get into the secondary phase, it's good to measure at the hub height and do 80-meter towers. And we're selling a lot of those as well. A rule of thumb, too, is that if you have very simple terrain, very flat terrain, yes, you use one 80-meter tower. If you have more complex terrain, it's better to use more 60-meter towers. That's just statistically makes more sense. You get more data. The tilt-up towers are definitely easier to install and easier to use, but different companies have their own preferences of either using lattice towers or tubular towers. These are some pictures that are from our customers. Do I have a? I don't think. Oh, yeah, but I do. I just wanted to note, for instance, these are two 60-meter towers that were delivered to a very remote site. They're delivered all in one pallet, and they're installed within one day by 2 or 3 people. This is a very complex site where tilt-up towers go up very easily. And same here. The only equipment needed is a truck with a winch to tilt it up. So these are just some trends of how the tilt-up towers work. Another important issue for towers is also they must be certified. And if you're not using a tower that has engineering drawings, you should be very careful about that. The tower configuration itself is becoming much more important. This is a big trend. It's not just what sensor you use, what data logger you use, it's the whole thing. So it's the configuration of the tower, measuring the temperature at the top and the bottom of the tower is very important. Redundancy, that's just cheap and obvious. Always use redundant sensors. Vandalism's a problem, so tubular towers are easier to deal with that. If you're going to do that, a lot of people use solar resource assessment sensors. If you're going to be measuring wind, you might as well put a pyronometer there to see what the solar radiation is. But the bottom line is that for bankability, consultants are looking at the traceability of the data from the actual sensor to the data logger, to who installed it, to how it was installed, to how it was communicated back to the headquarters and how it was analyzed. Everything along that chain is very important. You could have a really, really good class 1 sensor and it could be installed poorly on a bad boom and it's going to be bad data. So the entire process is very important. Bankability. I'll move on to remote sensing trends. I think I may be getting close to my time here, but remote sensing has become a lot more accepted in the United States. The trends that are the actual specific devices, some are approved more than others. There's LiDAR, there's SODAR, but I can tell you that 100% of the developers in the United States now use remote sensing in their resource assessment campaigns as part of it. And the fact that it will be in the IEC standards really shows that that technology is maturing. And one last thing is that there is a dual purpose as well, that companies will buy, they are expensive, buy remote sensing for wind resource assessment, but also use it post-construction at the wind farm to measure a power curve. This is a very important trend in remote sensing too, is the sheer uncertainty. This is becoming very important as well. In other words, we want to know what the wind is doing throughout the entire rotor area. You may have very high wind speeds at your tip and very low speeds at the bottom of your blade, and that can affect which type of turbine you choose. But all of this is very important to go upstream to measure this type of take these type of measurements in your wind resource assessment campaign. And really, finally, the return on investment is pretty good. So my point here is that remote sensing really has become more mainstream than it was just a few years ago. My second to last slide is some of the challenges that we have in the USA and Turkey are very similar, and we at NRG are happy to discuss these with you. We've been doing it a long time, but real briefly, access to sites is always one. I love this slide, using a donkey to get a tilt-up tower into a very remote region. The United States, like Turkey, has some very wide open places for wind farms, but there's always some other places that are very hard to get to. Security is always an issue. People like to steal the PV panels. Probably one of the more important bullets here is the installation expertise. We've learned that it's really important to hire professional installers. Just because somebody can install a cellular phone tower absolutely does not mean that they can install a wind energy tower. There's certain things about wind energy towers that are very important on how to install the boom the correct way and all that. So best practice is to hire professional wind energy tower installers. We all want our equipment now, and a company that can provide the towers immediately is very important. Safety is a big issue. I've been talking to people in Turkey now too. Over the past few years, safety has become very important. Data communication is always an issue. The windiest sites often aren't in sites where there's a lot of good cell service, so you have to have a good communication logger that will transmit the data even in a very low bar cell site, or use satellite. Budgets are important. Training and support is very important. And again, the bankability issue is very important as well. And you know, I've learned over the past year here that there has been, I say the Turkish experience, where people will do one measurement with one mast and apply for a permit, and they will win the bid, but they have a very hard time finding investors to help build their wind farm, because they look at the wind data and say it's really not bankable. I don't trust the data. I don't know where the tower was made. I don't know what sensors were used. So the point here is to use best practices, international wind energy at best practices, and to saving a few $100 or $1,000 may cost you very dearly in the long run. So anyway, there's a tremendous growth in both markets. I put this last slide in to make a point also too about the installation, and this is important too as far as the Turkish market and doing the first phase of measurements. If you do have, this isn't working, but anyway, you want to measure where the wind farm is going to be, and I know that in the first phase that's very difficult to do, but if you are measuring several kilometers away, you've got to be very careful about the data that you're supposing will be several kilometers away. So if you're going to put a wind farm in a certain place, measure at that certain place, because there's going to be a difference at a higher elevation than a lower elevation. I think I am out of time here, but my last slide is that it is a very exciting time in Turkey. Use best practices, use proven equipment. This is a picture on the left of a 60-meter tower on the back of a truck, just ready to be dropped off at a site and installed. On the right is a picture of a wind cube LiDAR system with a custom-made power source. We're here to help. We've been through a lot. We've been doing it for 30 years, and I'd be happy to talk to you about that. Hopefully this has helped you. Thank you very much.
Biz çok teşekkür ederiz.
We thank you very much. This, I think, has been quite a relevant presentation. Of course, in the United States and in Turkey, there might be similarities, but of course, there might be points that we are not quite alike. Probably we would need some specific engineering work to be done, considering the facts of the country. I think that will contribute to the future of the industry. Accurate measurement by using accurate devices, but also what is a must is to make the measurements in the right place. Of course, the best location where you can identify the potential of wind power is number one rule. That would apply to many of the countries, but of course Turkey and every country is unique to itself. Therefore, the problem of the lack of accurate measurements in the accurate place might be a big problem for Turkey. I think this needs to be taken into consideration during the measurements. Now, I think we need to move on to the next speaker. Mr. Santivilla will be our next speaker from AWS True Power. He is the lead engineer, and I would like to introduce him briefly. Since 2000, he's been involved in the wind power industry, and has been involved in development, consultancy, and site identification fields. Also, he is engaged in measurements, also wind flow modeling, turbine design, and other fields. Also, he's a graduate of the physics department of the Barcelona University, particularly in the renewable energy systems. He is the lead engineer in AWS True Power currently. He will be giving us an insight into his experiences globally, I guess.
Good morning to everybody, and pleasure to be here. My name is Santi Villa, and it was said, and I work for AWS True Power. Just allow me a brief presentation of my company. AWS True Power is a consultancy in solar and wind power, which has been in the industry for more than 25 years. We're active internationally in a number of countries and actively working also in Turkey. In terms of what we do, from the very beginning, the company specialized in providing and developing and providing solutions, defining solutions for the problems that we're encountering. Okay, so that's what we try to provide, insight from science to provide solutions to practical problems. And my presentation, in this particular case, will be a solution we are proposing and providing for a particular aspect, which is a wind flow model. Okay? So wind flow model, and wind flow model uncertainty. This one. Okay. So let's talk about these two very important aspects, wind flow model and wind flow model uncertainty. They are completely related, as you know. Wind flow model, this is extremely important, because as you all know, you'll be measuring initially at one point just one met mass location, and then you will have to extrapolate that into 5, 10, 15, 20 turbine locations. So you'll need to use a strong advanced wind flow model to extrapolate your measurements from the mast to your turbine locations. That's as you all know, that's not an easy task. And related with this, the more complex this task is, then the more impact this will have on your modeling uncertainty. Okay? Modeling uncertainty, as you know, is typically the largest component of your uncertainty. You can measure very well, you can measure at half height, but still, if you've got only one mast and you need to extrapolate those values to 20, 50, 20, 25 locations, then that's a big step, and that can multiply your uncertainty. And therefore, experience shows that modeling uncertainty is the largest component of uncertainty. And this component will have a direct impact in your P90, which will be your basic value when financing. So this will have a direct impact on your project finance conditions. Having said all this, having seen the importance of modeling uncertainty, then what we can say is that this is a topic that has been traditionally not as rigorously as quantified as it should be. So what we're proposing here is a methodology to be objective, to be able to objectively quantify modeling uncertainty, and then to extract the power of this method in the benefit of your project. So, but before going to this new approach, what is the industry currently doing for assessing modeling uncertainty? Well, basically, 3 aspects are considered. First one is distance. So the larger the distance between your mast and your turbines is, typically it is assumed that the larger your uncertainty will be. And this sounds good, this sounds logical. Second aspect is complexity of your site. So it is also assumed that the larger the complexity of the orography, of the wind conditions, the atmospheric conditions on your site, then the larger will be your uncertainty wind flow model. And finally, more than a factor, a technique that is used very widely when you have more than one mast on site is to produce cross predictions between masts, because then if you check how one mast predicts the other one, that can tell you about how your wind flow model is performing, predicting the wind speed at your turbine locations. Okay, so distance and terrain complexity. But is this really the only factors, or are these the main factors that drive modeling uncertainty? Well, we believe that these factors are important, but we think that we should address them in a better and more comprehensive way. Okay, and let's see an example. Well, in this example, we have a very nice site, or at least very nice image, where we can see a mountain. If this was a wind site, we would really consider this as a very complex site, okay? But despite this, let's take a look. If we were walking along the ridge of this mountain, just really flat ridge, probably the wind resource there is not expected to change too much, okay? We could walk quite a long way, and still the wind, we could be experiencing a similar wind. So this would be that long distance along that direction would automatically involve larger modeling uncertainty. Whereas on the other side, if we simply take 20 meters, 50 meters, 100 meters down the hill, that will definitely involve a very strong change in your wind resource, and at the same time in your uncertainty, in your potential errors when extrapolating. Therefore, this would be an example where large distance in one direction doesn't involve large uncertainty, whereas small distance in another direction definitely involves larger uncertainty. So therefore, what we are proposing is a new approach, is a different approach. Well, what we are saying is, yes, distance and complexity are very important, but we believe that if you have a model to represent, a wind flow model that represents your wind resource, then you should base your modeling uncertainty on a different concept. You should base your modeling uncertainty on what we call wind resource similarity. Okay, and the idea is basically that the more similar the resource is in 2 points, then the easier will be for the wind flow model to predict one as a function of the first one, to predict the target as a function of the referent, to predict the turbine as a function of the mast. Okay, so let's take another step and see how we could implement this new approach, this approach based on wind resource similarity. Okay, so how could we do it? How could we objectively quantify, put numbers into this proposed approach? Well, and our thought was to propose the following. Well, if you typically, when you measure wind, you are interested in wind speeds and wind directions, then if we want to compare points in terms of wind resource, we need to compare wind speeds and wind directions. And following this, that's what we did. We propose 2 parameters, which we call speed deviation and direction deviation, to objectively quantify the difference in wind resource between 2 points. Okay, and we propose those expressions, those mathematical expressions, that could be seen as indexes of similarity. Okay, the higher those indexes, the more different your points will be, and therefore, the more difficult it will be for your wind flow model to predict the turbine starting from the mast. Okay. Okay. So these are at this point these are just two parameters, two proposed parameters. The next step we did was to try and translate this into reality. Okay. We wanted to test this. We wanted to put this into a practical way, into practical shape that was useful, that we could use for projects to improve the knowledge of projects. Okay. So what we take this approach and we apply it to a number of sites and covering more than 70 data from more than 70 met mass and in a number of different climate conditions. We process all the data, we analyze all the data, and we were looking for statistical relationships between that data. And okay, what was the final conclusion we got was that distance, despite being a potential predictor for wind flow modeling uncertainty, was not statistically independent. Whereas if we consider speed deviation and direction deviation, these two parameters, we have good indicators, good predictors for wind flow modeling uncertainty. Okay. So we, up to here, we've seen how we could translate those parameters into objective quantification of the wind flow modeling uncertainty. And allow me just to one small comment here, which is very important. This methodology, however, relies on having a good description of the wind flow of your site. And to do that, the only way to do that is to have what we could call to apply an advanced wind flow model. And what does an advanced wind flow model mean? I mean, if your site may be experiencing different effects depending on the area you are, then you need a wind flow model, an advanced wind flow model that is able to capture all those phenomena. It is able to capture orographic, topographic phenomena that depend on the shape of your site. You need a model that is able to capture roughness phenomena. But you also need, and very important, you also need that your wind flow model is able to capture atmospheric phenomena, because a site is not only driven by the topography, it's also driven, and very much, and we will show a couple of examples, by temperature changes, by pressure changes, by all these atmospheric conditions, okay? In our particular case, AWS True Power applies a model we call site wind, which is an advanced wind flow model, which has been tested for more than 10 years, 15 years, in a number of cases, producing very reliable results, okay? Just as a very small description, this is a model that is composed by two sub-models. Mesoscale model, which is the model that should capture all the atmospheric phenomena of the site, coupled with a microscale model, which is the one that finally refines all the results. Okay. So to here we have a proposed way to quantify modeling uncertainty, and we've mentioned that it is really important to base this approach on an advanced wind flow model. And then the question is, okay, and we've done all this, but how can we use this in the benefit of our project? Well, we identified, or we proposed three main benefits. If you can quantify the modeling uncertainty at your turbines, well, you will be able to objectively define what is the contribution of your modeling uncertainty. But not only that, if you are able, again, to quantify the modeling uncertainty of each turbine location, this will give you a picture, and will show you a very graphical picture that with your met mass, you may be covering the wind resource at your site, but you may realize that with your mast, you are not covering it enough. And maybe you can decide that you need another mast or another more mast, okay? And finally, well, if this was the case and you had the time to install a second mast, then go ahead with it, because that will increase your knowledge of the site and the value of your project. That will increase your P90. But let's suppose that you don't have that time. Still, you can have a benefit, because if you know the uncertainty associated with each turbine, then you can take your decisions when designing turbines. You can see two turbines that are seeing the same resource, but if one of them has much lower uncertainty than the other one, then select the first one for your turbine layout, because that, again, will decrease your uncertainty and will increase your P90. Okay? So these are key key benefits your project could receive of an approach like this. Okay, so this is finished theory, and let's go, how can this be useful into real projects? First project, this is a project which we could call of a medium complexity. It's not extremely complex, as you can see. This is representing the topography, and the site is dominated by a ridge, a small ridge. It's not a mountain, it's just a hill in the middle that goes from south to north. And the elevation goes down to the sides and to the north, okay? And this site was instrumented with 4 masts. Okay, this is a real site. Okay, so there was a reason there for installing 4 masts there. But just as the first guess, what would have happened if the developer had relied only on 1 mast? Okay, so let's translate this site, applying the side wind model, an advanced wind flow model. Let's translate this into an uncertainty map for each mast. Okay, and we get a result like this. Okay, these are 4 images of uncertainty maps. And just as a quick interpretation, in these images, green and pink colors mean low uncertainty. Whereas as you move into brown and darker colors, you'll be increasing your uncertainty. Okay, so what's the conclusion from this? Well, the conclusion is that the 4 masts are representing mainly their area around them. Okay, not the mast to the west is obviously not representing the mast to the east. The mast at the top of the ridge is not representing the mast, the resource at the bottom of the ridge. Okay, so this is a clear example where you can objectively see that 1 mast wouldn't be enough to produce a reliable estimate of this site. Okay, but the combination of these 4 masts led us to this scenario. In this combined scenario, we combine the information from the advanced wind flow model and these 4 mast locations. And what this is telling us is that with these 4 masts, the site is fully described. The wind resource there will be extremely well described. Okay, so this is a very visual example of the benefits of an approach like this to decide on the suitability of your measurement. Let's move now into a second test case. This second test case was a much more complex site. Okay, this I'm showing here is just a small part of this site. The whole site was something like 40 by 40 kilometers. It was a huge site, and it was composed by initially about 20. Well, they were installing more and more masts, but we started with 20 masts, and we ended up with about 40 masts on this site, and the capacity there could be over 1 gigawatt. Okay, so this was a huge site, very good site. Okay, but this I'm just showing a very small part of it. This is the image at the top is showing the resulting uncertainty map for the site when taking into account all the mass, and is showing also the contour line. So you can see that there is. Let's see this. This is a sort of plateau. This is relatively flat, and then there are very, very steep areas down here, okay? And just for reference, this is about 5 kilometers, okay? And and for this site, for this huge site, we applied the advanced wind flow model. We applied the side wind, and we got a preliminary result, which is a map of raw wind speed, which means a map of speeds that have not used any met mass measurements, okay? So that was the first benefit, and this is shown for this area here. So this image here is a map of raw wind speed that doesn't use any measurements. And in this map, to interpret this map, you should take into account that when a color changes, it means a step of 0.5 meters per second. Okay, so you can see that there was a huge increasing gradient of wind speed going to the west. Okay, okay. So we have this huge site, this very complex site, and also very complex in terms of atmospheric phenomena that were happening there. And that's why we zoom into this small part to show two examples of atmospheric phenomena there. Okay, so, and one of the questions we made here ourselves was, well, the site is pretty well described. We have green, we have pink everywhere, but when you get, something that you observe is that when you get to the very edges of the plateau, oops, no, sorry, my apologies, wrong button. When you get to the very edge of this plateau, you get a sudden increase in uncertainty, okay, of modeling uncertainty. And one, for example, that calls the attention is this one. Okay, so that's 4 kilometers. That seems to be flat. What's going on there? Why is the uncertainty going up there? Well, if you recall from our proposed approach for modeling uncertainty, we mentioned two parameters, speed deviation and direction deviation. Well, in this particular case, in this particular 2 points, what we can see there is that in 4 kilometers, there's a huge wind speed gradient of 1 meter per second, okay? Two colors there, 3 colors, 1 meter per second of speed gradient, which is, in 4 kilometers, is a huge speed gradient, okay? And the good point about this is that we can see this gradient in the results of the raw wind speed, of the speed map that doesn't use any metadata, okay? Well, but you could tell me, yeah, your model is predicting this without using measuring data. But is that real? Is that happening there? Well, the good thing about this is that the client was concerned, the developer was concerned about this very particular position and decided to install an additional mast there, which was good for us because we could see in the real measurement that the speed gradient was real. I mean, it was really impressive seeing that in such a small distance and such a, in theory, simple conditions, we had that really strong atmospheric phenomena. Okay, so one first case where an advanced wind flow model can, like SideWind, can capture really important atmospheric phenomena. And just allow me one more case in the same area. Okay, we see one. What happens there? Okay, there we can also see an increase in uncertainty in an even smaller distance, and there is not such a big gradient as in the previous situation, okay? So what happens? What's the reason for the increase in uncertainty there? Well, again, if we recall, the approach was talking about speed deviation and direction deviation. We see that speed deviation maybe is not critical here. So what about direction deviation? Well, what we did here was to, again, look at the results at the raw map, wind map, okay? And the model here was telling us that there was a shift in direction between this point here and this point here. The model was predicting that very shift in direction. And again, you could tell me, yeah, your model is predicting that, but how do we know about it? Is this real or not? Well, again, the developer was concerned about this aspect, decided to install a metmast there, okay? And again, it was really good, confirming that, as you can see, there is a real shift in direction between this location and this location. A shift that is not observed between those two locations there. Okay, so just the final conclusion of this talk, what our recommendation would be, measure as accurately as you can, but at the same time, use an advanced wind flow model, an advanced methodology that can reflect all those complex atmospheric phenomena. Thank you.
Sayın Vila'ya çok teşekkür ediyoruz. Detaylı, kapsamlı.
Thank you very much for this comprehensive presentation. Now, we will have the next speaker, Mr. Harold Mellinghoff from Devi Group. You know, they are component and they provide certification studies for component manufacturers. So they are providing lab services with a well-developed background. Since 1990, Mr. Mellinghoff has been working for Devi, and also he is working in the wind measure. He was working in the wind measurement service. Later on, he had works on calibration, power curves, etc. And at the same time, he is been working as a member of the group of the standard. Also, after the merger with UL, he has been working as the service manager. Mr. Mellinghoff is now the engineering manager.
Can you hear me? Yeah, okay. Yeah, thank you, Mr. Speaker, for the introduction. I may have a short correction. You said since 1990 I'm in the business. That's not really true. I started working in 1999 for Devi, so too much of an honor. Anyway, I would like to see if I can take you through the development that we took in Devi and me personally in wind measurements, and then going over to power curve measurements. I think those are aspects of a development of a project in Turkey where it may be helpful that we share some experiences. So the outline for today's talk is I would also try to cover a bit the ideas, what we learned from wind mast placements, and then would go into power curve testing, what we learned from the winds in Turkey, what that means for typical sites in Turkey. I would briefly introduce the classic approach of power curve measurements together with the site calibration, and then go over to the current standard power curve testing and warranty conditions that we find in contracts, which are very important when you start thinking of signing the contract, not when it's already been done. I would like to give a brief example of what it means if your wind speed information at hub height is biased, what that means for the AEP of your project. And then I would like to introduce some new concepts, or well, they're not too new, but they're in the standard now. That's the IEC 61400-12-2, nacelle-based anemometry, where we see some interesting development, which is remote sensing and spinner anemometry, plus some ideas how we think we may improve the accuracy of the measurements and help finding acceptance for that. So a similar task as the colleague has already introduced. Here's a wind farm in Turkey where we see the colors, meaning the height maps, and a typical size of Turkish wind farms is 50 megawatts, about that. And now the first question would be, where do you put the towers? And there's two approaches that we follow at Devi. One is like the educated guess. You ask an engineer who has been doing quite a lot of that before for regions where you would think that a tower is required. The second one is that you look into first what is Masnet saying. For simple terrain, they tell you about up to 10 kilometers you can have one representative tower. For complex terrain, the recommendation is 2 to 3 kilometers. But as the colleague already mentioned, the terrain complexity is a very important ingredient. So we also used CFD methods. This is an example from Reynolds solver, so it's not having the full atmosphere, but also allowing you to study what the simple effect of the terrain is onto, for example, in this case, a slice that you go through the terrain, and you will already see effects that you don't get with a classic WASP-based calculation. So one thing we have here is a spot in the middle. Let me see. Is this one the pointer? Yeah. So this red spot is where you have compression of streamlines, and it tells you that that's on a rim that you have high wind speeds. You can even have negative shears there. And right behind you see an effect that you would also observe, for example, if you have a stone, a big stone in a river, you see behind that stone there's slow flow and also recirculation. So the message I want to give you here is, if you have the time and the willingness to do a CFD study in advance, it can tell you already on possible locations where you need to be prepared for critical wind conditions. Here's an example how important wind measurement directions and exact wind measurement directions are if you are in complex terrain. We have a site which is stretched along a rim. It looks very much like a saddle. The white crosses are the turbine locations. It's 11 locations. And at the black cross we had a Met tower. Now, one study that had been made, suddenly when they changed the wind direction by 5 degrees, they saw the output of the model, which is for the turbines in the northeast, in a different color, that gave suddenly 10% more wind potential at that site. And it was hard for the people to understand that, in detail, why this small change in direction suddenly has such a dramatic impact. It's basically something that you can see from CFD modeling, that small changes sometimes at other locations have nonlinear impacts. But also in this case, we saw that the weighting from the direction gave us the reason why it's why those turbines had been giving a different weight. So if you assume a certain wind direction which is off by 5 degrees, it can have dramatic impact on the average. If you go over all the cases that you have in your study, you do them with 5 or 10 degree steppings. Now, I would like to do the steps towards power curve measurements and first briefly reintroduce the concept of power curve measurements in flat terrain, following the standard of the -12-1. On the left side, you have this setting. You have a Met tower which measures wind speed at hub height. You have your turbine. You measure wind speed and power. You correct for air density. And then you get a data set which, after bin averaging, would give you a power curve as it's expressed in the lower left corner. For complex terrain, the standard foresees that you first have a measurement phase where you put up 2 towers, one at the location of the turbine where the turbine is going to be, and the other one which will be there when the turbine is in place. The important thing is that you need to do this measurement in advance. So once the turbine is there, the standard recommends, if you want to do a power curve test, take away the turbine, put the mast there, but nobody will ever do that. So if you don't do a measurement of the site calibration, and you will later want to have a chance following this currently active standard, then you must consider that well in advance during the installation of the wind farm. But then the idea is that you describe with a single number per direction bin, and the typical spacing is 10 degrees, the correction of the wind speed at hub height. Now we know that this is not really true, especially if you're in complex terrain. The profile may change more than on different layers in different amounts. So similar to the overspeeding effect that you get when you have a hill, on the lower parts of the rotor you may see stronger site calibrate or impacts from the terrain than when you go up. Anyway, this is the standard that's still there, so people who make contracts now may very well be looking into that. Let me give you a brief overview what it means if you have a bias in your wind speed of a power curve test. Now you see a lot of curves here. The red dotted line should be the one that we get started with. That should be a turbine that's not really available on the market. I modified an existing curve, but let's assume that this is typical for a 2 megawatt turbine. And now I ask myself, what happens if I assume that the wind speed measurement has been biased in steps of 2% from 90% to 110. And those are the power curves I get, and the cutout that you see here has to do with the fact that the type I try to work with also had a cutout hysteresis. And when I then go into a calculation saying, okay, let's assume my wind speed is biased by, for example, 2%, and I take an annual average wind speed, which is on the right side, the different wind speeds as they are defined in the IEC, then I get an AEP misconception, let's put it like that. For example, for the 4-meter case, 4-meter case would be this line, the blue one. It's the most dramatic impact. And at 98% of your actual wind speed, you would be somewhere between 5 and 10% of misconception. The actual number is for 4 meters that you are at 6.3% misconception of your energy that you get from that measurement. So the message I want to give you is that the wind speed is the most sensitive parameter in a power curve test. But wind speed is not only one thing that can change the power curve. There are other parts that can have dramatic impact or significant impact on a power curve. So most two important ones are wind shear and turbulence intensity. With wind shear, it depends on the magnitude that you have. It can improve your net output or it can decrease it. It depends a bit where you are. The standard that's upcoming introduces a concept which is called rotor equivalent wind speed, which is intending to neutralize different wind shear measurements in a power curve test. Sorry. Turbulence intensity is another important factor. If you have high turbulence, it helps the turbine to start operating, but it will also reduce when it reaches the rated power value. So the net effect is often such that you have a reduced net output of the turbine. Temperature range is meant to cover uncertainties that come from icing of sensors. If you do the measurement well, you can have ways of detecting if you have influences from cold temperatures. If you have dry air, then I think up to -10 degrees, there's no issue in measuring at cold temperatures as well. Tilted inflow has an influence reducing the power curve. So simply by the fact that you have less energy similar to tilted solar irradiation onto a panel. So it reduces also the impact. All of those are situations that you can see in Turkey in a power curve test. And now when we look into the warranty formulations that manufacturers use, they have the idea that they try to give a warranty for standard conditions, which is understandable, saying, okay, we warranty you for a certain frame of turbulence, shear, tilted inflow, the power curve. Yet the problem is, if you have a car and it's not performing, on a gravel road, you can take it to a highway and test it there. With a wind turbine, you will probably not do that. So the question is, who, the investor or the turbine manufacturer, should take which care of adopting this power curve warranty to a realistic case. And our recommendation here would be to ask the manufacturer before you sign the contract if he can give you a warranted power curve designed for that site, so that turbulence, shear, all parameters that he wants to have as limiting factors, and have that part of the contract. Other parts that influence the measurements are status signal definitions, and sometimes we find clauses which can make the whole evaluation rather vague, that says if you find some hint that this factor influences the power curve, you should do further tests, you have to filter anymore. The bottom line is the more filters you have and the less strict the formulation is, the longer the measurement can take, or it may even be impossible to conduct a power curve test under certain frame conditions if you have also a complicated site. Oops, sorry, I was a bit quick. How can I do? So I would like to spend some more minutes on what alternative measurements are currently developing in the market for power curve testing. The first one is a LiDAR, which is looking horizontally, and the model from Avent is shown here on the left. That's a picture taken at the offshore Fino 1 site in a research campaign. The idea is that the LiDAR looks upwind and you have the rotor, and when two of those beams have free line of sight, the device can produce a measurement value in distances where 2.5 rotor diameters are possible. It gives you a horizontal wind speed, a yaw misalignment, which is very attractive, and with that you can have a wind speed value at a height. Sorry. The other alternative approach which is currently coming is spinner anemometry. This is a picture taken from a manufacturer that is currently introducing this technology. The model is, in terms of dimensions, the spinner is a bit small, but the principle is clear. You have sonic anemometers which measure the flow on the spinner. At this point, there will be a slowdown from the basic back pressure effect. On the other hand, the spinner itself is an obstacle which compresses the flow to the side, so that gives a speed up effect. The net impact of all those three sensors would then go to a computing unit which produces a common value for the horizontal wind. Nice side effects is that you have yaw again, so the direction of the wind. There is discussion that they think they can also measure the tilted inflow. And the good news is that this is already something that will soon be applied in the standard. So the existing standard 61400-12-2 already allows spinner anemometry. There's a refinement required how to calibrate those, which is currently discussed in the expert team and will soon be available. And then there's LiDAR remote sensing. I think we may hear more about that as well. This is a system installed in our test site. It's a LIASFA V2 device with an independent power supply. The basic idea here, is that you scan not just one level but several levels, and that will be the big change in the upcoming standard of the revision of the power curve standard, and will introduce the concept of rotor equivalent wind speed. The way the LiDAR will be used is still in conjunction with a MET tower, but it may be a MET tower that has a height of 40 meters, mainly to monitor that the device is not drifting. Sorry. And here's some data or a setting of nacelle anemometry where we added two further anemometers. So to the left and the right on those circles, you see the serial sensors which don't have moving parts. And in the center, there's a wind vane, and to the left and the right, we added some Teeth first class advanced sensors for which classification is available. And the measurement has been taken at this location where we look towards offshore winds. I will come back to some data from that later. Looking into the options that we currently have in power curve testing developments and measurements, I tried to do this summary. Now I don't know how well readable it is. The first two lines are the classic settings that we now see. That's the MET mast and flat terrain following the current edition of the -12-1. And that's probably, if you have a contract for a wind farm for turbine supplies, who will probably refer to that, plus additional requirements that the manufacturer may define. Then you have nacelle anemometry. It basically gives you a point measurement at hub height. That's the same idea that the classic standard follows as well. Spin anemometry has the same ideas and will probably soon be available. The vertically scanning LiDAR is the one introducing the rotor equivalent wind speed, and we expect that the standard is going to be ready maybe this year or beginning next year. This nacelle-based LiDAR, looking forward, that's more into research. But I think there's a strong chance for using this technology in offshore, because putting up a Met tower in offshore is extremely expensive. But offshore investments are the ones that are even more expensive than onshore. So it makes sense to find ways to do power curve testing with a small uncertainty. But we are touching areas where research is still giving us important input. The cell-based LiDAR onshore, I think, has the problem, or an additional challenge, that as the turbine tilts and rolls, the measurement point that the LiDAR sees will be sort of leveraged in distance. So here we come to the question, how does the LiDAR respond to possible changes in the terrain? And that links it to questions, can we correct with, again, CFD models, the data read from the LiDAR, understanding how it generates a value that we finally use in the data set of 10-minute averages. For me, that's a field of research. One thing that's even more advanced is using a nacelle-based LiDAR that scans several heights. That would also allow for rotor equivalent wind speed to be used as a wind speed definition. But I think we have good chances that, like in 3-5 years, somewhat in that time, there will be enough know-how in the community that we see this coming also in warranty conditions. Basically, manufacturers are rather reluctant to experiment with warranty conditions. They're the most conservative part if you discuss measurements there. Bit data from the one setup I just saw you about nacelle anemometry. I had two settings here. One was the sensor that came with the turbine itself. It's the green line, and the red one is from the additional sensor, and the met mass wind speed is below. So we see that the correction depends significantly on wind speed, both correct on an order of magnitude of 5%. They later align to higher wind speeds. So my first conclusion was, yes, the position and the sensor has quite some impact. But with the two sensors that we have, we can also study what the sensitivity is if you move that thing sideways, because the whole uncertainty that comes with the measurement and the definition of the position of the anemometers on the nacelle is very, very sensitive. So if we could have arguments saying, even if we don't produce it with 1 or 2 centimeters accuracy, we know how sensitive it is, we can use that as part of the uncertainty calculation. That would help us. Next slide here is, so one part is how big is our correction that we apply to the signal that we measure. The second question is, how big is the standard deviation? If the standard deviation is low, it will help us say we can have a better confidence in calculating the free wind that we need for our calculation. And from the setting with, again, here now we have in red, sorry. In red, that's a signal of the additional anemometers. We see that the error is basically slower up to like 12, 15 meters, where the input on a power curve is most sensitive. Afterwards, the picture changes, interestingly. But I think with those additional sensors, we have a good chance to minimize or to further reduce the uncertainty that we get from using cap anemometers on the nacelle. The second point is we have a classification The sensors that we had there didn't have the serial sensors don't have a classification, so we would need to have high uncertainty assumptions for that. Okay, and then one last point from that data set. Interestingly, you would think that if you have a passing rotor passing your sensor every 3 seconds, you have discarded all your information about turbulence intensity. In fact, where it matters most, turbulence intensity on the mass being on the y-axis, between 5 and 15%, you still have some correlation. The average line is the blue line that you see there, the green line with the blue line being the standard deviations. So it is not completely destroyed, which was interesting to see for me. Again, we used the first-class anemometers for this study. And with this, I would like to come to conclusions. So one thing I wanted to show you is that mass placement decision is a very important step at the very beginning of a wind farm development, and we think that CFD studies can help finding good or important spots. Met towers placed for wind measurements are not necessarily suitable for power curves. That's one question we had. Occasionally, somebody had been measuring the wind with us in a one-year study and now wants to do the power curve test. But due to space requirements, it's often not that you can use that. If you want to do this, then you need to check that when you design your wind measurement campaign, but you would need to have a final layout of the wind farm at that stage as well. And as far as I know, designs of wind farms, especially in Turkey, change as you progress in the development of the project. Power curve verifications are an important tool to know the value of the wind farm asset and to keep on maintaining it at an optimal state. So when you want to have a chance to make a complaint against a manufacturer, when you think you have underperformance and the turbine is an issue, then you should be able to do the measurement following the contract you have signed. And we have seen cases when people say, yeah, I signed following classic IC. Now I want to do the test because there's some questions after 2 years of operation. If they hadn't done the site calibration in advance, they had basically given out of hand the chance to execute that test. Fulfilling the measurement conditions in Turkey is often demanding and requires planning ahead for site calibration at this point. The use of alternative verification methods should be negotiated together with the sales contract. So if you want to do that, then when you buy the turbine and the wind farms, that's the time you should talk about that. In terms of acceptance, I think the best chances are there for the nacelle-based methods and the remote sensing with a highly complex terrain in Turkey. I don't think that you will find manufacturers that now accept remote sensing methods in highly complex terrain. And nacelle anemometry is undergoing promising developments that help reducing the uncertainty. And with this, I would like to close and thank you for your attention.
Sayın
Thank you very much, Mr. Mellinghoff, for this presentation. I think these recommendations in your final slides were quite remarkable. We have just gone beyond the 15-minute time for the speakers. Maybe we'll be extending the session. Mr. Ayşel Berger will be the last speaker. He is from Vaisala company based in Finland. They are providing services in the wind energy sector. The speaker started working for Vaisala in 2000 and still he is the offering manager and energy assessment department of Vaisala. Throughout his experience, he worked in energy capacity assessment, product development, production, and management. And before his position in Vaisala, he was a research officer in Washington University Atmospheric Department. Dr. Ayşel Berger has been working on the climate change and the effects of climate change in this direction. Thank you.
Well, thank you for the introduction and the opportunity to speak to you. I will try to keep things brief, given the time constraints that we're at, and hopefully find the presentation of interest. So today we'll talk a little bit about using uncertainty to drive campaign design. Some of the ideas and concepts that we're presenting here are been talked a little bit about from previous presentations, so hopefully some of the concepts will maybe be familiar by the time we're done with the session. So we'll start with just kind of a very broad picture here of the wind development process and kind of the major steps that you want to go through as you go through and work your way towards having a due diligence level wind energy assessment, starting from project mapping and layout design, moving into Met campaign design, and then going through collecting data, analyzing that data, making your energy estimates, finally getting towards your investment decisions with a due diligence analysis. Today we'll talk just about two steps and primarily focus on the Met campaign design, but talk also a little bit about initial layout design and how those two are interrelated. So starting with preliminary layout design, we feel that it's actually very important to always have the end goal in mind. And to be able to help move in the right direction, we feel it's very important to start with the initial layout design as one of the very first steps that you would actually do in project development. We feel that that's quite important for us just because, as other speakers have mentioned, we really care about the information at the turbine locations. And so once we can come through and define where we're going to put the turbine locations, then that will allow us to be able to start having real quantitative conversations about where do we go through and best determine how to measure at the project site to be able to best understand the wind resource at that site. So in optimizing Met campaigns, we often have clients that like to go through and put their wind masts at the very windiest spot on their site. And we understand the inclination to do that because it allows you to understand like the greatest potential at your project site. But if the wind turbines aren't going to be able to be placed in a similar location, then that measurement's really not as useful as potentially could be. And so for that, we very much suggest that the Met campaign needs to really go through and support the turbine layout. And exactly, what do we mean by that is that we need to be able to go through and help make sure that the measurement locations are in the best locations for reducing uncertainty with respect to the final assessment analysis. So if we go through and start to really think about things in terms of uncertainty, we can go through and look at how uncertainty changes as we go through and change our measurement locations. We can run very many scenario analyses to be able to go through and understand, given this particular layout, where are the absolute best locations for us to be able to go through and place measuring devices, again, with that goal of being able to reduce uncertainty to the lowest possible levels. To be able to really go through and understand uncertainty, it's important for us to talk for a minute or two here about what do we mean when we say we want to use a comprehensive uncertainty framework. Some of our prior speakers have talked a little bit about uncertainty and specifically with respect to flow modeling. And that is definitely very important, but it is also just one component of the total uncertainty at a particular project. You have measurement uncertainty, you have vertical extrapolation uncertainty, modeling uncertainty, but also power modeling uncertainty, and of course measurements. But it's really important for us to be able to understand, how do all of these different processes actually interact with each other, make sure that we're going through and understanding uncertainty from every single aspect of the analytic process. And what do we really mean by that is that, some of the specific aspects of uncertainty that we want to make sure that we capture within our uncertainty framework is that we take into consideration the full configuration of the Met towers. As other speakers today here have talked about, the Met tower configuration is extremely important, and we need to make sure that we actually go through and properly account for all the different ways that your Met tower configuration will impact the uncertainty. Using multiple sensor levels, being able to understand the distances between those levels, how that impacts our estimations of the shear profile at that met mast, and then our vertical extrapolations above the met mast. Also talking about mounting uncertainties, how are the booms oriented, are the booms the proper length, are they attached to the tower correctly? All of these things that are maybe relatively mundane can have very large impacts on the measurements, and the measurement uncertainty can then carry through to all the other uncertainties within the analysis. So we also want to be able to go through and properly account for remote sensing devices. They are very useful measuring devices at sites, and making sure that we actually really understand how best to be able to utilize the remote sensing data in concert with the MetMass data, as well as our modeling data of the flow regimes, is a very important aspect of things. And then lastly here, we really want to make sure that when using a comprehensive uncertainty framework, we really understand how these uncertainties interact with each other. How do they play in concert with each other? We need to understand, what uncertainties are independent from one another, while what uncertainties are actually dependent on each other. As an example of this is that we can think about maybe measuring uncertainty. If we have relatively high measurement uncertainty for whatever the reason may be, maybe we have very short booms on the met mast. If we have that high measurement uncertainty, that uncertainty at that particular level will interact then with our vertical extrapolation uncertainties. And so we'll end up with a potentially higher uncertainty up at the hub height level. Once we have a higher hub height level uncertainty, that potentially can impact our ability to be able to understand the spatial modeling uncertainty because our uncertainty is so high. And so it's important to really be able to have an uncertainty framework that be able to understand each individual component of uncertainty, but also then to be able to have covariance models that be able to allow those different uncertainty components to be able to interact with each other. It's a very important aspect of being able to really have a solid view on what the uncertainty is at a particular project site. So what does this mean? What do we mean when we talk about uncertainty, and how do we go through and utilize this to be able to go through and place met mass? So we'll show here over kind of a series of the next few slides a project wind farm. This was in the United States, but is applicable to many sites. The concepts are very similar. And we show here each orange dot represents a potential turbine location, and the size of that orange dot represents the uncertainty at that particular turbine location. And so currently in this particular demonstration, we're not showing any on-site met towers at all. There's no on-site measurements, and so our uncertainty across the project site is relatively uniform. It's also relatively high. And we have to base our assumptions on uncertainty based on more regional data than site-specific data. But as we go through and, say, start our measurement campaign and we introduce a met mast shown by the yellow square, we can see that there's a dramatic reduction in uncertainty, not just at locations near the met mast, but also at locations potentially a little bit removed from the met mast. And as our prior speaker have talked about, you can be able to go through and understand what the uncertainty is across the site and be able to make reductions not just at the met mast, but also at locations that are potentially a little bit removed from that location based on similarity of the wind resource and the terrain complexity. So we get one met mast in, we get a nice reduction in uncertainty. We still have some pockets of higher uncertainty across the project site. And so then we can make recommendations that, well, we should go through and install, a second met mast at the site. That helps us again to be able to reduce uncertainty. And if we continue down this process and say, okay, well, we've now reduced uncertainty a little bit more, but we'd still like to be able to see, a lower overall project uncertainty, we can add in a third met mast out here on the eastern side of the project. And then finally we can come through and say, okay, well, maybe we need one more, kind of up in the northwest to be able to get kind of a nice uniform picture of uncertainty. And then the last step here is just showing that, well, we could potentially add in a fifth met tower into this site, but we can see now that the reductions in uncertainty are becoming much smaller. And so it may not necessarily be cost effective to always go through and, say for this particular layout, maybe only 4 met masts are really required. So another way to kind of look at this data is in terms of kind of a time series plot. So we can go through and make these recommendations about exactly where to place the met towers. We can also make recommendations about what is the best way to be able to go through and look at the uncertainty over time as we go through and collect more of this data. And so this is kind of a graphical representation here showing uncertainty on the y-axis and then time on the x-axis. And so what we can see here is that shown as the status quo is basically we have our wind farm with just a single Met tower on site. And we say, okay, well, with just one Met tower, what do we look like for project uncertainty? And we're at about a 13%. And that's pretty good. And maybe that's good enough for this particular, financing. We generally hope to be able to get uncertainty levels, for a very good pre-construction due diligence assessment. We're hoping for uncertainties that are in the, the 8 to 10% range. And so how do we go and get into that range for this particular example? And we showed as previously, we can go through and get the largest drop there with just adding in the second Met tower. And then we get, kind of decreasingly smaller results, reductions in uncertainty as we add that third and the fourth Met mast. But we can also go through and see, okay, well, how do things change with time? And this can be a very valuable tool for our clients because it helps them, one, have an understanding of what does the total time frame look like to be able to get to that due diligence level Met campaign. Is it going to take us a year to get there? Is it going to take 2 years? It's very site dependent, but it's information that we can provide to our clients. We also can work with clients as well if they have to be able to develop a wind farm under maybe certain time constraints. They need to be able to hit a certain incentive and the wind farm needs to be getting constructed before a certain time limit. We can go through and then work under that constraint and say, okay, well, how much can we reduce the uncertainty given the time constraints that we have? Or potentially also work within budgetary constraints. If a client has a specific budget that they need to be able to hit, how best can we go through and reduce uncertainty within those budgetary restraints and understand how best we can go through and make recommendations about Met towers or remote sensing devices. So really the point here is just that uncertainty is a communication tool, and it's something that we talk with our clients all the time to be able to help them best manage the risk at their project sites. So in summary here, we'll just kind of recap with our suggested approach. And really we want to start with the end in mind. We always want to think about how can we best go through and reduce uncertainty of your due diligence analysis. That's our primary goal. That's all the conversations that we have with our clients. That's what we are always striving for. And the best way to be able to start having those conversations in a quantitative manner is to be able to develop a turbine layout, even if it's a preliminary layout, very early on so that we can go through and start having very real conversations about the exact turbine locations. Then choosing, your measurement locations, again, with having that aim of reducing uncertainty. We don't just want to go through and measure the windiest spots. We want to make sure that there's a good combination between the measurement sites and your turbine locations. And then it's paramount to be able to go through and use an appropriately complex uncertainty framework to be able to guide this whole process. If you have an uncertainty framework that is just too simple, you're not going to be able to go through and make the correct decisions. And then lastly, we want to be able to move forward with this Met campaign, and we definitely want to be able to move forward with confidence. We want to be able to know that as we go through and spend all the money and take all the time and resources to create this Met campaign, that we're going to end up hitting our desired target for total project uncertainty. And that's really kind of our final goal that we want to be able to get to, is that when our clients work with us and get to the final due diligence level assessment, we want to make sure that there's no surprises there with uncertainty. We want to make sure that we've all just worked together to be able to come through and have a very solid assessment campaign for the project to be able to get financed. So that's all I have here for today. I appreciate your attention, and thanks again for the opportunity to speak.
Thank you very much, Mr. Eichelberger. This brings us to the end of the presentations. I think we have almost half an hour. We can get to questions now. Please introduce yourself and please just tell us who you are asking the question to. We have a mobile microphone available in the hall.
Size de sorabilirsiniz. Ben belki
Maybe I forgot to introduce myself by a hurry. My name is Sabahattin Öz. I'm from the Ministry of Energy and Natural Resources, Department of Renewables. I'm the head of the department. I'm sorry for this late introduction of myself. Is there any question? Yes, Zeki? Microphone is not working. I cannot hear him without a microphone.
maybe I speak in English. Okay, so I think they cannot hear it, so I will tell it in English. So thank you very much for this session. It's been, I think, very fruitful, and I believe maybe this session is the most important session throughout all the conference, because all the speakers, they mentioned that this is the first critical step to start investing into a wind park. So this is the measurement. It has to be done right, with proper instruments, proper installations, proper reportings, and it has to represent finally a bankable study. I don't know if you have any idea, but today in Turkey you can apply to wind licenses every year, and the only request from you is to have one measurement mast in place according to some regulation we have. How you're gonna erect it, the instruments that you're gonna use onto it, and how it's going to be the height, and so on. But we also know that with only one single mast you can apply up to the maximum capacity of the region, which is nowadays is something like 260 megawatts, if I'm not mistaken. So what would you say about this? So is it logic, or it makes sense to apply with one single mast up to 260 megawatts, and then, I mean, what will be the effect of this application, this sort of application, to the remaining life of the investment, the start of the investment, and also to the investment? Thank you very much.
Cevap vermek isteyen var mı? Buyurun.
Can the translators hear me?
Yeah, I do now.
I mean, personally, for me, I guess one word or one phrase would be to do it very carefully. Again, from the American experience, I cannot conceive how you can bid on a 200 megawatt project with one wind tower. It's that fundamental. So I would say, at least, as I said in my speech before, if you can do 2, 3, or 4, do more Met towers. That is going to increase the likelihood of you being more accurate. And also, as my colleagues had said, use CFD as well, and just put more money into the upfront assessment, and don't be cheap about it, because I've already heard this week of some people that have produced wind farms and they're losing money because of that very issue. And so it's that simple as far as I'm concerned.
Yeah, if I may have a short comment. As far as I know, there are many sites in Turkey when not just one investor is going there, but several. Everybody puts up its own tower. Everybody's on a high pressure to have a very cost-effective measurement. I think it would be interesting, but it would be a general question of changing the policy if there is an information exchange between those who measure at the site. But it's a completely different approach. But then I guess if you could have use of all the information that's available from a site, you would already have those 5 towers possibly. But then you need to have a fair exchange of the one who then finally wins the project and can do that. But on the long term, I would expect that this would help making the project that is then realized be more feasible in terms of financial constraints. But that's something that policymakers would need to think about.
Yes, and I definitely want to agree with both of the other two comments here, that it is, it's very important. And I think, Greg, you hit on a really important point that we really want to, as consultants, we're very concerned about underperformance of projects. And we want to make sure that we come through and suggest, pathways where we can go through and avoid that. And definitely a solid net campaign is an absolutely great way to start off on that right step. And so there's definitely concerns about very limited MET campaigns. Very limited MET campaigns lead to higher uncertainty, and higher uncertainty can open the door for potential project underperformance. And I think your recommendation here as well, to be able to hopefully have some data exchange between partners, would absolutely help. But it's often the case that developers don't like to talk to each other, at least not about their MET data. So hopefully we can find a solution though.
Yeah, just to add a short comment on this. As you saw, this is just as you mentioned, these are basic rules that in some way the ministry has to set up, to give recommendations to set up minimums, okay? And as you mentioned, one MET mass for 260 megawatts really doesn't make much sense, but one MET mass for a smaller project, 5 megawatts, 10 megawatts, it could be okay. The comment I would like to make here is that, well, there are some regulations, and probably they are minimum regulations, and probably they need to evolve to cover different scenarios, but at the same time, it's also the developer responsibility to take decisions and decide whether those minimum conditions are enough. Well, they may be enough to get licensed, but are they enough to make your investment and your return really profitable? I mean, is that information you have from the site enough to provide the compensation you have to give to the government? So to me, as Dave mentioned too, these are minimum conditions. You should, but it's also the responsibility of the developer to make the right decisions to get as much knowledge as possible, the minimum knowledge required about the site to get the right return of the investment. Okay, so sometimes minimum is not enough.
Teşekkür ederim.
Thank you. I also would like to add a few points. Actually, all of the speakers have highlighted quite remarkable points, which I all agree with. The legislation in Turkey provides some minimum requirements, as mentioned by the last speaker. In other words, on the point of measurement, I think there are some requirements stipulated by the regulation, and we have to consider the fact that it has not been a while that we have made the last amendment to the legislation. I think in the next period there will be some amendments to the legislation that will bring along also the outputs of the measurement and the requirement for making an application together with the outcomes of the application has been a mature idea, but of course you might guess how long it has taken us to bring it to the mature level. Zeki, you would know the incubation period takes quite a while for these discussions, but at least we're at that very point, and I have to say that at least the major institutions, agencies have reached a consensus with the Ministry of Energy as a result of the experiences. But the last point is important. Of course, for 260 megawatts, single measurement, single mast measurement is not enough. But you would know that the developers just not confined with this one mast. But if you push through the limits, one measurement for all for every 50 megawatts, this would again be misleading. I mean, it's not just a matter of having as multiple masts as possible. What is important is to have the measurement that might have the capacity of representing that site properly. Of course, hopefully we're getting to there. Any other question we have?
Herkese merhaba.
Hello, my name is Abdullah Görür from Enercon Sign Assessment Department. I will be asking in English.
To Mr. Villa. Honestly speaking, I quite find interesting wind flow modeling uncertainty. It was quite interesting analysis. My question is, have you ever, so the wind flow that you've used must be probably the AVC true power modeling tools that you analyzed in your analysis. I was wondering, have you ever done any comparison with other commercial CFD modeling to do how good they are, the representatives surrounded by the mast locations? I mean, any benchmarking analysis, I mean, how far they can be predict the more good modeling surrounded by the area?
I'm sorry, I wasn't sure about that. I think your question was related with whether we've done comparisons between the performance of the model and in terms of distance. My apologies, but I couldn't hear it very well.
So in one slide you showed that there were 4 masks on the side, and the sides and each mask surrounded by representativeness. How good in terms of to keep the uncertain limit? And I was wondering, this analysis must be done by your CFD modeling or your flow modeling. I was wondering, what if you use some other commercial packages, how far they could be able to representative of the area? I mean, they might be, I don't know, maybe good, maybe not. Kind of benchmarking analysis, I mean.
Yep. The examples we show and the methodology we propose, I would first make comment. I would make a first comment, sorry. First, the methodology is conceptual, and it tries to provide and introduce a different approach. Okay, we just want to say, look, distance is not everything. You may be close, but the conditions may change a lot, or you might be far, and the conditions may not change that much. Okay, so that was first idea behind this concept. Then the implementation of the uncertainty model had to be based on a particular model, wind flow model. Okay, and that's because when you apply this uncertainty model, the one we describe, you do it in base of the results, results of the model. Okay, so you want your model to describe the phenomena that happen in your site. And with that description that doesn't use any metmass data, and then combine with the measurements, real measurements from the number of projects with more than 70 mass I mentioned, then we were able to calibrate the uncertainty model with the measurements, okay, and to get a practical expression for the modeling uncertainty. So having said this, we believe the approach is replicable to other wind flow models, but in the way we implemented it, it's specific for our system, which is the Sidewind, which is the one we normally use and the one we trust more, and the one we best know, of course, because it's the one we apply. Okay, so the answer would be, no, it hasn't been really applied with other models, but having said this, what we have done in the past in parallel is to compare the performance of different wind flow models. That we have done, okay? And with the aim always to see what model is able to capture in the best way, the local phenomena.
There's another one over there. I can see a hand.
Thank you all for your presentation. It was quite interesting, I think. I am Otto Barton from Darwin, wind turbine manufacturer from the Netherlands. I have a question for the last speaker. In your graph you showed that you were able to reduce the uncertainty in wind speed measurements from 13 down to 8%, if I'm correct. Of course that's very nice, but 8% is still quite a big uncertainty, I think, even with 5 wind masts. So what do you think is the biggest source of this leftover uncertainty?
Yes, thank you for your question. I think the main thing there that I probably failed to properly explain was that the uncertainties that we were showing in that last graph were in terms of energy, not in terms of wind speed. And so that's the primary difference there. The overall wind speed uncertainty would be probably on the order of around 2% or so. And then when combined in with the 2% in terms of energy, and then combined in with the all the other uncertainty components of the analysis, then you end up with a total energy uncertainty in the range of kind of 8 to 10%. So that was not a wind speed measurement uncertainty, that was an energy uncertainty, which is will explain the difference, I think.
Do we have any other question? Which is not the case, so thank you very much for your participation. I would like to thank the panelists, and we have certificates that we are going to give out to the panelists, and this will be the tokens of appreciation. And when it comes to wind, of course, naturally the token of appreciation would be a model of wind. Thank you.